Hello students, welcome to lecture of Kinematics and Theory of Machine. Myself Professor Patel, and we are going to continue our first chapter, Simple Mechanisms. Topic we will cover in this lecture is inversion of single slider mechanisms. Okay, there are five inversion of single slider and we will cover all of that. Okay, let's start. Okay, let's start inversions of single slider crank chain, and among them first is pendulum pump, or it is also known as a bull engine. So as we studied, first of all, in any mechanism, first start with the counting the number of links. So first is the link number 1 as this piston rod with this piston. Same type of second piston will be here, not shown in book, but there is a two piston and piston rod, all will be considered as a link number 1. And after that, second link will be this crank, okay, and third link will be as a connecting rod. So that's how these four links are connected. And you can see in this animation, double acting means both piston and connecting rod moving with in single motion. Okay, so we are going to next inversion of a single slider. Okay, it is a oscillating cylinder. In oscillating cylinder, the piston and piston rod and this piston is totally fixed together, so they are moving together, counted as a link number 1. Okay, after that you can see the link number 2 is a crank. Link number 3 here is totally fixed. This link number 3, or I can say this frame, is fixed. And link number 4, which is moving in this case, is a cylinder. Cylinder is moving. Okay, let's see in animation. So you can see here, this piston and piston rod is moving together. There is no relative motion between piston and piston rod. Yes, cylinder is oscillating. That's why this inversion is known as oscillating cylinder. Okay, for the next inversion is next inversion is a rotary internal combustion engine or NOM engine. Okay, so you can see here there are 7 cylinders are there, but we have to consider any one of them for the counting of the link, not all 7. Otherwise you will say there are lots of pistons, 7 pistons, 7 connecting rod. No, only we consider any one. Only we consider any one of this cylinder. Okay, let's count the number of links. So first of all, link number 1 is a cylinder here. Link number 1 is a cylinder, first cylinder. Link number 2 is this piston. Link number 3 is a connecting rod, and link number 4 is this crank, or I can say the whole frame, which is fixed. Here crank is not rotating, whole cylinder is this whole frame is rotating in this case. Let's see the animation. Okay, in this animation you can see here all cylinders are fixed, but you can find the NOM engine in that. Some NOM engine are that in that this is the fix, and this whole cylinder is this engine is rotating. Okay, I will send these links in our group so you can see that how this cylinder is rotating. Okay, in NOM engine. So most important inversion from the single slider is quick return mechanism. So there will be two quick return mechanisms are there and very important, and based on there are examples also there in our book. So first inversion in a quick return, you can see crank and slotted bar, crank and slotted lever quick return mechanism. Let's start. So first of all, what is the quick return motion, and why it is required? So first of all, check this. You can see on a screen, this is the shaper machine, okay, which is used to use for the slots and keyways and all that. So in that you can see it is cutting from the top surface. So if I am saying that this is the length of the block and I want to cut from the top surface, from this top surface I will put my job here and it will remove material from the top surface. So what I am saying, if it cut from the top surface and after that this tool is returned to its initial position and after that it will return again. So if there is a same time used in cutting and returning, then will be half time you can consider is a wasting. So for production wise, if you want to decrease the time in a returning, this mechanism is developed, quick return mechanism. And in this mechanism what will happen, like if you say this is cutting in a t second, then it will return in a t.5 second. Means it will return speedily because there is no material to cut, and in a cutting stroke it will remove the material. Okay, so its return is very speedy and in cutting it will be slow. So how that can be possible with a constant velocity, constant RPM motor, means motor is rotating at the same speed. So for that you have to understand this mechanism which is known as a crank and slotted bar. So first of all, you can see here the crank. Okay, this is the you can see the crank, and at the end of this crank you can see this piston here, or you can say the slider, not piston but slider, which is located in a slotted bar. You can see here this is the slotted bar here, in which that if crank is rotating in some direction, what will happen, this crank slotted bar is also moving in this direction, it will force this ram in this direction and cutting stroke will happen. Up to which point? Up to this point, when crank will be here, this ram will be its extreme position, and after that when this crank is rotating up to this point, in this position this ram will be at the extreme point here. So that's how it will happen. Okay, so why it is a quick return mechanism, you can see from these 2 points. Check this is the extreme point of the crank when our ram is here, or you can say here. This is the extreme point for which our cutting stroke end. So this is the angle for which our ram is returning. This is the angle for the cutting. So during the cutting stroke it will complete this large angle, and during the return stroke there is a smaller angle. So difference in these two angle is proof that the crank and slotted lever is a quick return mechanism, and it will save the time in our production. Okay, so that's how this machine, shaper machine, works. You can see here is a disc is connected. Disc means crank, and this is a slotted bar. You can see it's in black color. So it makes it moving, and you can see the angle, some angle I am showing you. From this is from up to this, this is the um, this is a returning stroke. During this angle it is returning, and during from this to this angle it is cutting. Okay, let's see. Okay, it is a simple animation of this mechanism. You can see here from this point it is returning, and from this to this point it is cutting. So this is the large angle, here is a smaller angle. Okay, after understanding this figure, we are going to solve some examples. There are 2 or 3 examples in this chapter, so we will solve that. Before solving that, we are going to understand this figure properly, because totally geometrical relation used at examples. So first of all, in this figure you can see here what is this. This is the position of the crank. You can see here crank is right now in this condition. Okay, but when this crank is rotating and reach at a B2 point, which crank position will be here, this, and our ram will be here. Okay, and this slotted bar will be reached up to our P2 point, and same as when our crank will be here, the slotted bar will be in this condition, and this ram will be here. Okay, so this is the 2 position shown in this figure. This is the extreme position of lever or slotted bar, and you can see this is the extreme position of the crank. Okay, so when you are calculating the example, you have to draw the extreme figures also. This intermediate condition means at a P point condition not required during the example. Okay, so during example we don't need this detailed drawing, only we draw this simple drawing. Okay, and we understand what are the terms. So this is the crank position. Okay, this is the lever, you can see here, this is the lever, and you can see here this is the stroke angle and this is the return angle. So this total angle is a alpha and this angle is a beta. Okay, so half angle will be here, half angle you can see this is the alpha by 2, and you know that it is the here 90, so this angle will be 90 minus alpha by 2. Okay, so before starting the example, what in our examples asked for, so there is a ratio, means what time reduced by using this mechanism. So there is a one ratio asked in our example is a timing of cutting stroke divided by timing of return stroke, means it is a ratio of the timing during the cutting and return. Okay, so you can see here the beta angle is here, this is the beta angle, so it is the cutting angle, and total this is the return angle, which is the total angle alpha. So time is totally depend upon this angle, so we not calculating the time because we need only ratio. So we will find this ratio by measuring this angle. So how can you find the beta and alpha? We don't need to find both angle. If you using this geometry, this triangle, and you find the alpha only, as you know that if you find the alpha you can, or you can find beta, any of two. Okay, and if you find the alpha you can find this ratio directly. Okay, because total angle is a 360 minus alpha is equal to beta. So these two formula we will mostly use. Okay, so let's start for the example. So as you can see the given data, so So crank and slotted lever mechanism used in shaper has a center distance. So first of all, before going to further, check what are the distance. Center distance means you can see this is the center of what? Center of crank. Okay, this crank is rotating with respect to this C point, and you can see here this A is a center of this lever, because this lever is moving with respect to this center. Okay, and crank is rotating with the C center. Sometimes this AC distance is also given, A to C distance between two centers. Okay, so in this case this distance is given, which is 300. Okay, and center of oscillation of slotted lever and center of the rotation of the crank. Radius of crank is 120. Find the cutting ratio. What we find, we are going to find this cutting ratio. Okay, cutting to return ratio. So as this figure is, we know, and in all example of this chapter we have to draw this figure so we can solve this example. Okay, after that we find the alpha from this data. What we have given in this, you can see this is the center distance. So we have given the distance between A and C. Okay, this is given 300. Okay, what other data is given? You can see the crank 120. So radius of this given, and means distance is a 120. Okay, let's start. So first of all, as you know that you can see here, this is angle is already known, because this angle is alpha and this angle is 90. We know that this angle is a 90 minus alpha. Okay, as you know, sine 90 minus alpha by 2 is equal to opposite side CB1 divided by AC, and both value already given in example, which is 120 and 300. So it is a 0.4. Okay, so we take the sine inverse of 0.4, which is a 23.6, and as you already know, this angle is a 90 minus alpha by 2. So what will happen? 90 will come in this side, and we find the alpha, and alpha value of alpha is equal to 132. You already means you know that if you find the alpha, this ratio will be finded easily. So we have find the alpha is equal to 132.8. Put this in formula, you will get the answer. Okay, so simple answer is a 1.72. Okay, this is the ratio of the time of cutting stroke to the return. Totally geometrical. We have to consider the triangle. Okay, in crank and slotted lever quick return motion mechanism, the distance between the center distance is a 240 mm. Length of crank is 120. Find the inclination of slotted bar with the vertical in extreme position and time ratio, cutting stroke to return stroke, and length of slotted bar is also given. Okay, so first check what is the data given in this example. So first of all, 240 in center distance is given. This distance is given. Okay, which is 240, and after that crank is given. So this distance is also given, 120. Okay, and 450, this length of this slotted bar is also given, which is 450. Okay, so these distances are also given, and what we have to find, first of all we have to find this ratio, same as last example. What we will do, during the finding this ratio, we consider this triangle A CB1, this triangle, and we already know that 90 minus alpha by 2 is here. Sine is equal to opposite upon hypotenuse AC. Both data is there. If we find the alpha, the ratio will be easy. 360 minus alpha divided by alpha. Simple. So length of stroke is also asked in his example, and for that we have to use another geometrical relation. So first of all, find the ratio of the cutting to return, okay, which is same as the last example. Okay, so this is the data already given, and you will take the sine angle for this triangle, sine 90 minus alpha. So check this, it will be C1 upon AC, which is given 120 here and 240 here. So it will become sine inverse 0.5, and angle you find here is a 2. Angle you have find it here is a 2. It means that if total 1, it means that half time is saved during the returning. Okay, so let's start the finding the cutting stroke length of cutting stroke. So for that we have to consider this triangle, because you check this figure. Okay, so first of all check this figure, and you already know that during this R1 extreme point, this is the extreme point of our stroke, these 2 points, and with respect to that there is a P1 and P2. So ultimately you find the line of stroke, you can find the P1 P2, because P1 P2 and R1 R2 are same. Okay, so we have to find this P1 P2, and you know that angle already, because this angle is known, we have already find that. So what we can do, we can find consider this triangle. So we will find the P1 Q. We will find this P1 Q multiplied by 2 is equal to P1 P2, and P1 P2 is equal to line of stroke R1 R2. So first of all, considering this triangle A Q P1, we will find the P1 Q multiplied by 2 is equal to P1 P2. Okay, let's start. So check this, in this triangle you know that this is in this triangle you already know this angle. So this distance we want to find, and this distance is already given, this is the 450. Okay, and angle is known, so we will find this distance. Check this. Okay, so this is a very simple example. We have to consider this triangle. Okay, so there is also another example in our book, so practice that. Okay, if any query, ask me. Thank you. Okay, let's start our next inversion, which is the Whitworth quick return mechanism. Same as a slotted bar, but there is a orientation of links and all is minor different. You can see this is the assembly. So first of all, you can see the slotted bar here. The slotted bar you can see here. This is the slotted bar. In this slotted bar, the crank, you can see the crank which is rotating. This crank is rotating, and you can see there is a piston, and with respect to this piston, this whole slotted bar also rotate, but the center of slotted bar you can see here, the center of crank and center of this slotted bar is different in this case. So what will happen when this crank is rotating, it will push the this slotted bar. Okay, and this P point is connected to ram, and that's how this whole slotted bar will rotate with respect to this D point, and P point will rotate. This P point will rotate here. P point will rotate. You can see two circles in this figure. Okay, basically two circle. One circle is this larger circle, which is indicating the path of piston. This is larger circle is a path of piston, and with respect to that, this P point is rotating. P point on this slotted bar, which is connected to RAM, is rotating here. The smaller circle is a path of this P point, which is connected to RAM. So when crank position will be here, the slotted this our RAM will be extreme position at, and when this crank is rotating and reach to this point, okay, extreme this point, what will happen? At this point our RAM will be, so line cutting stroke will be here. So cutting stroke will be like this, okay, between P1 and P2. P point rotate, and P1 and P2 of position, there will be R1 and R2 positions. Okay, same as the slotted bar. So what is the angle? You can see there is a difference between this and Whitworth and the slotted bar. Check here. First of all, during this point, extreme position, and during this P point, when there is a P point here, our slider will be here. So, and during returning up to this point, our slider will be here. So there is this angle, you can see beta is smaller and alpha is larger. Beta is a smaller and alpha is larger. So in this mechanism, for cutting time upon returning time, equation will be alpha divided by beta. Okay, and beta is a smaller, so it is a returning angle which will be at the bottom. So difference between that, in our slotted bar there is a what? Beta upon alpha, and in this mechanism there is a alpha upon beta. Okay, so this is our last mechanism, and I hope you understand and try to draw this mechanism, because there is only two mechanisms can be asked in 7 marks individual. This quick return and slotted bar, which is very important and asked in 7 marks. Otherwise all other mechanism are 2 or 3. Draw 2 or 3 mechanism, combine and give you 7 marks. But these two quick return mechanism are very important. So practice it very well. Okay, thank you.